The universe continues to expand endlessly, stretching its vast fabric further into the unknown, a phenomenon that never ceases to amaze us. In 1929, scientists uncovered a profound truth: the very chemicals that compose our bodies were born in the fiery cores of distant stars. By 1957, humanity began to realize that the night sky was more than a breathtaking view, it was a mirror of the universe's unimaginable power and complexity. Every day, we gaze up at the stars, often oblivious to the intricate and dynamic events unfolding in the cosmos above. We constantly find ourselves pondering the mysteries of existence. Why are we here? Why do planets and stars exist? And what other possible destinies could have unfolded? Yet, despite this curiosity, humanity has a tendency to ignore looming issues until they reach a critical tipping point, even when these problems could profoundly impact us. One such celestial enigma lies in the dramatic changes observed in Betelgeuse, one of the largest stars in our visible sky. This colossal star has recently shown alarming signs of instability, trembling in ways that suggest something extraordinary, and perhaps frightening, is occurring. Betelgeuse, long the subject of fascination due to its gargantuan size, is so immense that it dwarfs our Sun, making the latter appear minuscule in comparison. It is no ordinary star, it never has been. Betelgeuse is a red supergiant, and it exists at an incomprehensible distance from us. Though it appears relatively close, it lies more than 640 light-years away, a staggering distance that highlights the sheer vastness of our cosmos. To put this into perspective, even if we could travel at the speed of light, it would take over 640 years to reach Betelgeuse. With our current technology, such a journey would take more than 12 million years, far exceeding the entire span of human history. This immense distance reminds us of the magnitude and grandeur of this trembling star, which has been unsettling astronomers with its recent behavior. Despite their serene appearance from Earth, stars are anything but quiet. Beneath their radiant surfaces, they are roiling with dynamic and often violent activity. Scientists are still trying to decipher the mysterious signals emitted by Betelgeuse, a star classified as a pulsating red supergiant. For decades, Betelgeuse's brightness has been observed to vary in cycles, shifting over periods ranging from 10 days to more than 100 days as the star expands and contracts. These gradual pulsations offer a glimpse into the dynamic nature of the star, revealing that it is far from static. What makes Betelgeuse even more intriguing is the dramatic fluctuation in its brightness, which can range from a faint magnitude of 5 to an almost dazzling magnitude of 0. These shifts occur in distinct cycles, with the shortest lasting about 185 days, while the longest stretches over 2,335 days, a testament to the star's complex rhythms. Occasionally, these variations align in more regular patterns, making them easier to measure and analyze with precision. In February 2021, astronomers noted that Betelgeuse's brightness had dipped to an unusually low value, recording one of the dimmest measurements in recent years. This sudden deviation from its usual luminosity not only caught scientists' attention but also underscored the star's enigmatic nature. Adding to its allure is Betelgeuse's fiery red hue, a characteristic that stems from its relatively cool surface temperature of about 3,500 Kelvin. While this temperature is significantly lower than the Sun's 5,500 Kelvin, Betelgeuse's sheer size compensates for its cooler nature, making it one of the most prominent stars in the sky. Despite its immense size, Betelgeuse emits less energy per unit area due to its cooler temperature, which somewhat diminishes its overall brightness. Historically, Betelgeuse has been relatively stable for a pulsating giant, but its recent transition to a more unstable state has left scientists concerned. This growing instability is linked to the star's core, where hydrogen, the primary fuel for nuclear fusion, is gradually depleting. As hydrogen fusion slows, the outer layers of Betelgeuse begin to expand, causing the star to swell to even larger proportions. During this phase, helium accumulates around the star's core, leading to a secondary fusion process known as helium envelope burning. In this stage, helium atoms fuse to form heavier elements like oxygen and carbon, releasing bursts of energy that counteract the gravitational forces attempting to collapse the star. However, the fusion of helium is far less consistent than hydrogen fusion, resulting in irregular surges of energy that destabilize the star's structure. These surges cause Betelgeuse's outer layers to expand and contract erratically, creating the pulsations that are observable as changes in its brightness. As these pulsations release enormous amounts of energy, they generate powerful stellar winds that strip away mass from the star's outer layers. These winds, characteristic of red supergiants, play a critical role in Betelgeuse's evolution, reshaping the distribution of matter and energy within the star. The result is a pulsating rhythm, reminiscent of a heartbeat, as the star alternates between periods of expansion and contraction. To decode these celestial phenomena, astronomers rely on advanced observational techniques such as photometry and spectroscopy. Photometry measures the intensity of light emitted by the star over time, allowing scientists to track its fluctuating brightness. Through photometric data, researchers can directly observe the pulsations of Betelgeuse, offering valuable insights into its internal processes. Meanwhile, spectroscopy analyzes the light spectrum emitted by the star, revealing critical details about its temperature, composition, and motion. When Betelgeuse pulsates, its spectral lines shift, providing clues about the underlying mechanisms driving these pulsations. By combining photometric and spectroscopic data, scientists construct a detailed picture of Betelgeuse's behavior, bridging observation with theoretical models. Astrophysicists go a step further, employing powerful computational models to simulate the star's internal workings and predict its future behavior. These simulations delve into the equations governing the star's structure, fluid dynamics, and nuclear processes, creating a virtual laboratory for exploring stellar evolution. One fascinating process occurring within Betelgeuse is stellar convection, where energy generated in the core rises to the surface in massive currents. This convection not only balances the star's internal processes but also influences its external luminosity, creating the pulsations we observe. As hot material from the core rises and cooler material sinks, these convection currents transport energy outward, altering the star's brightness. These currents, combined with the rhythmic expansion and contraction of Betelgeuse's outer layers, create a dynamic interplay between gravity and radiation pressure. Gravity pulls the star's matter inward, while radiation pressure, fueled by nuclear fusion, pushes outward, maintaining a delicate balance. This tug-of-war drives the star's pulsations, causing it to appear brighter during contraction and dimmer during expansion. As Betelgeuse nears the end of its life cycle, these convective and pulsating behaviors grow more intense, signaling the approach of a dramatic finale. Eventually, the star will exhaust its nuclear fuel, leading to a catastrophic supernova explosion that will mark the end of its existence. Until that day, Betelgeuse continues to captivate astronomers, offering a rare glimpse into the life and eventual death of a massive star. Its pulsations, though fleeting from a cosmic perspective, provide invaluable insights into the forces shaping the universe and our place within it.